Now, our next speaker, well, they're from Envio, which if you haven't heard of them, they're a data infrastructure provider that provides very high-performant infrastructure. And he's going to be presenting a case study on SwapX, kind of highlighting the integration of his tech with ours at Sonic. So please welcome to the stage Denham, the co-founder of Envio.
Thanks, Paul. Hey everyone, how's it going? So if we can go, we are on the beginning one, all right. If you're super excited about the high performance of Sonic, then you're going to be super excited about what I'm going to talk to you now. My presentation is on indexing millions of events in seconds. Just a quick show of hands, how many devs are out there in the audience? Builders, can even be vibe coders. Use ChatGPT once or twice. Awesome, okay. This is just a little teaser slide, something just to show you like the gravity of the performance difference, but I'll come back to it in a bit. First, a little bit about myself. My name's Denham, pronounced like the jeans. My academic background's in computer science and economics. Been playing around since gas prices on Ethereum mainnet were super friendly and you could experiment. A little bit more about me. I'm a safe guardian, a Puli holder, and a Grounds DAO member. Cool. By builders, for builders. Just to add a little bit of credibility to who we are, we're a team of 10 developers, been working in the space for a couple of years. We've built some production-grade systems holding well over $75 million, unhacked to date. And yeah, so coming back to Sonic, I think something that's extremely exciting, but also extremely scary from an infrastructure perspective, is the transaction throughput. So it is absolutely massive, and the existing Web 3 technologies aren't designed for this kind of speed. All right, coming back to this teaser slide, let's walk through it a little bit. So indexing is kind of like going through data, collating it, ordering it. It's a little bit like a librarian might put the books together in a library, so it's easier to find. Now, in this screenshot, we've got a benchmark results of indexing about 5 million events of a Uniswap v3 pool, and you can see the time taken to index these events. Now, notably with something like subgraphs, it takes about 17 hours, and with Envio, it's just under 10 minutes, so quite a massive difference. Out of interest, who here has used SwapX? Quick show of hands. Nice, okay. So I'm just going to run through a quick case study on what that would look like in a practical sense of high-performant data. This is their pair factory contract, and you can see it's deployed about 133 days ago, which is about 4.5 months ago. And it says only 51 transactions. However, that's 51 pools that have been created, swap pools. And that actually results in about 2.4 million events being emitted. And using existing technologies like subgraphs, this takes about 34 hours to deploy. Okay, not terrible, but not great. All right, but let's take a look at what that looks like with Envio. With Envio, it takes about 20 minutes. And this is what I deployed onto our development infrastructure, so it's not even the good chunky tech. But it really is chalk and cheese in terms of performance. It is a massive difference. To look at that more clearly, it's a difference between 34 hours and 20 minutes. Okay, so really quite a substantial difference. Now, that's great, but we're looking at data over 4.5 months. What happens in the situation in a year's time? You've got now, and we've got the 1-year scenario of 1 to 2 weeks to deployment, and that's based on linear growth or hopefully a little bit kind of compounding growth. And just think about it in terms of in 3 years' time. Look at the examples of like Uniswap v2 data, well over 2 months to deploy with subgraphs. And there's just the Envio comparison with the actual growth scenario, so it would be even shorter if it was just linear growth. Cool. Build bigger, ship faster. So we've touched on why we need it. We've touched on how much faster it is, and let's go through how we actually do it. A little bit of secret behind the sauce. So we identified 2 major bottlenecks with how you get data, okay? And this is how you currently get blockchain data. Usually you make RPC calls, remote procedure calls, to a blockchain node gives you some kind of data and returns it back. Now, this is perfectly acceptable with, let's say, Ethereum level transaction throughput and block times. So the two major bottlenecks we identified is one, network and bandwidth. You're sending JSON data over HTTPS. And the other one is application design. Nodes are designed for consensus. Getting data is more of an afterthought, but it works. But it's not very optimal. Anyway, introducing Hypersync. It's our version of a blockchain node designed for getting data. Mega fast, mega flexible, real time. We've got a lot of different things in our docs to play around with, sample. It really is some powerful tech behind the scenes. A little bit to look at what it's like. So we use flat files, Parquet. We heard the doctor talking about Sonic DB yesterday. In some ways quite similar. It's built in a low-level system language, Rust, very performant. And something to note is it doesn't perform consensus. This node is designed for getting data. All right, so I'm not going to dive into this for too long, but just to give you kind of a brief overview of what we're looking at. This seems almost too simple to be true, but most database designs are this kind of row-orientated database. It's the same as you have PostgreSQL, et cetera, et cetera. Now, really simply, all we do is take that row-based data and we flip it into columns. And you might say, okay, cool, but there's not much of a difference here. But it creates a massive difference in terms of reading and writing to disk. Literally just the way it processes and finds the data. And so for searchability, it's quite incredible how it can be just a massive optimization. How many Rust stations out there? How many Rust devs? Not too many. Oh, there we go. Cool. This is not a benchmark of Hypersync because there's no Hypersync instances built outside of Rust, but I thought worth showing too. These are different Ethereum clients, and Reth being the new fresh one, built in Rust, and you can kind of see the results it's getting being quite substantial. Cool, so we've touched on Hypersync. That's really the raw data engine that gives our systems performance. Really well suited to Sonic. If you're finding your existing infrastructure is lagging, definitely check it out. That's the engine that's making it fast. And then HyperIndex is kind of the more developer-friendly, catered framework for indexing specific smart contract data. That's usually a bit more dev-facing, and you use it to build APIs, a little bit like subgraphs. Just maybe an extra honorable mention is HyperRPC. So Hypersync is a lot more flexible, a lot more powerful for getting data, but it comes with its own API, which isn't always the simplest because you've got to switch from your existing technologies. And HyperRPC is an RPC interface on top of Hypersync. So really cool. Practically, HyperRPC doesn't address network and bandwidth because you're using that same kind of format. But in terms of application design, it's really quite fast. Cool, and we've seen some really cool stuff built with this technology. So we've got on the left, we have a headless block explorer, an account abstraction block explorer, in fact, that a dev built. And it doesn't have a backend. It simply makes requests to Hypersync on the fly. On the right there, we have something called Snub. If you've made a lot of transactions, you've been a DGen for a long time, forgot all your approvals, I definitely recommend giving it a try. It goes through a bunch of different networks and sees how many unlimited ERC20 approvals you've made. And it has nice links to revoke.cache to undo that too. But again, something like that's pretty hard to build, at least at that level of performance, without something like Hypersync. Cool. The one on the left is kind of a fancy terminal UI just to count events. And in this exact case, we're counting UniV3 events on mainnet, on Ethereum mainnet. And what I think is really quite powerful is you can see we're processing 490,000 events per second. Again, this over here, called chain density.xyz, you can pass in any smart contract address, select the network, say you want to get the transactions or event density. And a little bit like Google Analytics will give you user behavior on visiting your website, this will give you analytics on the distribution of activity on your contracts. Now, what really makes it impressive or possible with Hypersync is that it's doing it on the fly. There's not an existing database that's been running through things and saving all this data. So you can see, even on this contract, it took about 1.06 seconds. Bigger contracts can take a minute, but again, really cool to see that happening on the fly. Uniswap v4 data, on the right there's the actual indexer. You can see all the different networks it's syncing from. Hyperindex is a multi-chain indexer, so it's really nice to sync multiple data points into the same API, and truly super performant, something that can work with Sonic's high transaction throughput. And on the left here is actually a UI for that, and it's v4.xyz if anyone wants to check it out, but you can see live liquidity events as they're coming in. I think this was recently reposted by Uniswap too. Cool, lots of really cool clients and users using us, so I won't dive into too much. Gitcoin, Velodrome, ZK Pass. Some really incredible feedback. Don't take my word for it. Check out some of the feedback on our landing site. A lot of existing user feedback. And that is my talk. Check out the sites at envio.dev. That's our Twitter handle. I think it's also the same for Farcaster. And that's my Twitter handle as well as Telegram, if anyone wants to chat a little bit after this and chat about what they're building, some cool tech. All right, just on time, 3 seconds, 2 seconds left.